Hey there, have you ever stopped and just wondered how something like ChatGPT actually works? How it can understand what you're asking and then write something back that makes perfect sense? I mean, it really does feel like magic. But today, we're going to peek behind the curtain and break down the incredible engineering that makes it all possible.
Okay, so this is really the heart of the whole thing. You see, computers at their core don't get language. They don't understand English or French or, well, anything other than numbers. That's their world, math. So the big question, the giant puzzle we have to solve, is how do you possibly bridge that gap? How do you turn our words into their numbers without losing all the meaning along the way?
I mean, just look at something like machine translation. For an AI to take that English sentence, a cute teddy bear is reading, and turn it into the correct French, it has to understand the idea, right? It's not just a simple word-for-word swap. It needs to grasp the concept of a teddy bear, and that it's cute, and that it's reading. That's the real challenge we're going to dig into.
All right, so where do we even start with a problem that big? Well, the very first step, and it's an absolutely crucial one, is to figure out how to turn our incredibly complex language into something a machine can even begin to work with. And yep, that means we've got to turn words into numbers. This whole process really breaks down into two main parts. First up is something called tokenization, which honestly is just a fancy way of saying we chop the sentence up into smaller bits, or tokens. Then, once we have those pieces, we turn each one into a unique list of numbers. Now, that might sound pretty simple on the surface, but trust me, the real magic is all in the details. You know, how you chop up the text is actually a huge deal. For example, you could just split it by words. Simple enough. But then the model sees bear and bears as two totally separate things, which isn't great. Or you could go to the other extreme and chop it into individual letters. That's awesome for catching typos, but it makes everything incredibly slow to process. So, what's the solution? Well, most models land on a clever middle ground called subword tokenization. It breaks words down into common pieces, giving you this perfect balance of understanding the meaning while still being super efficient.
Okay, so we've got our tokens and we've turned them into numbers. We're done, right? Mission accomplished? Well, not so fast. Because if you just assign a random ID number to each word, you lose something absolutely critical: the relationship between them. The meaning just vanishes. Think about it like this. An early technique basically treated every single word as its own little isolated island. In that world, teddy bear is just as different from soft as it is from, say, rocket ship. But that's just not how language works at all. We know teddy bear and soft are related. So the real goal, the holy grail here, is to create these numerical representations, we call them embeddings, where similar ideas are actually represented by similar numbers. And that brings us to this absolutely amazing concept, word embeddings. The best way to picture it is like a giant, multi-dimensional map of language. Every single word has its own coordinates on this map. And the cool part is, words with similar meanings are clustered together. So king and queen are neighbors, dog and puppy are right next to each other. This is what breathes meaning into the numbers. It turns them from just random IDs into this incredibly rich web of connections. And here's the classic example that just blows my mind every time. With these embeddings, you can actually do math with the meaning of words. You can take the vector for king, subtract the vector for man, and then add the vector for woman, and what you get is a vector that is incredibly close to the one for queen. The model isn't just memorizing words, it's learning the relationships between them. This was an absolute game changer. So that's incredible, right? We've given words meaning in a numerical space, but we've only solved half the puzzle. Because knowing what a word means in isolation is one thing. The real trick is that a word's meaning can totally change based on the words around it. And that, my friends, is the problem of context.
Just take a look at these two sentences. The dog chased the cat chased the dog. We're using the exact same words, the exact same embeddings for dog, cat, and chased, but by just swapping the order, the meaning is completely flipped. The meaning isn't just in the words themselves, it's in the sequence. So how did engineers first try to tackle this? Well, one of the early approaches was something called a recurrent neural network, or RNN, and the idea was pretty intuitive, actually. It would read a sentence, one word at a time, from left to right, and try to keep a running memory of what it had seen so far. With each new word, it would update its memory.
But this whole one word at a time thing had a huge weakness, a real Achilles heel. Look at a sentence like this. It's long, it's complex. For the model to have any clue what it refers to when it finally gets to the word pounced, it absolutely has to remember the word animal from way, way back at the start of the sentence.
And, well, that's exactly where it fell apart. Turns out RNNs had pretty bad memories. By the time they chugged their way to the end of a long sentence, they'd often completely forgotten the crucial details from the beginning. This was a massive roadblock for the field, and it got a name: the long-range dependency problem. So the whole field was kind of stuck. They needed a new way of thinking, a new idea that could let a model see the whole sentence at once and understand those complex connections without forgetting. And what they came up with wasn't just an improvement, it was a revolution. And it's called attention.
I mean, think about it. For decades, progress was slow, step by step, building on these one-word-at-a-time models. Then, in 2017, one single research paper came out and just shattered everything. It completely changed the game and laid the groundwork for basically all of the powerful AI we interact with today.
And the title of that paper was just perfect. Attention is all you need. So bold. And it says it all, really. The researchers basically said, hey, you know those slow, clunky, one-word-at-a-time networks? You can throw them out. You can build something way more powerful using only this new attention idea. So what is this magical self-attention? Well, instead of reading a sentence like a person, one word after another, it's more like the model gets to see the entire sentence at once, in a single glance. And for every single word, it can instantly look at all the other words and figure out, okay, which of these other words are most important for me to understand this word, right here, right now. It calculates these attention scores to create a network of meaning.
The best analogy I've heard for this is the librarian. Imagine you're on a library. The topic you want to research is your query. So what do? You go to the card catalog and you scan all the titles, those are the keys, to see which ones match your query. Once you find the best match, you go and grab the actual book from the shelf. That's the value. The AI is basically doing this exact process at lightning speed for every single word in the sentence to pull in the most relevant context. Okay, so let's recap. We've got tokenization to chop up the words. We've got embeddings to give those pieces meaning, and now we have this incredibly powerful attention mechanism to understand context. You put all of those ingredients together, and what do you get? You get the architecture that is the engine behind pretty much every modern AI you can think of, the transformer.
A transformer is really a two-part system, a team working together. First, you have the encoder. Its only job is to read the sentence you give it. It uses that self-attention we talked about to build this super rich, deep understanding of what you actually mean. Then it hands that understanding over to its partner, the decoder. And the decoder's job is to take that understanding and start generating a new sentence, word by word.
So picture our sentence: a cute teddy bear is reading, going into the encoder. As it passes through, self-attention just lights up. The word reading instantly connects to teddy bear. The word teddy bear connects back to cute. All these connections are made simultaneously, building this complete, holistic picture of the sentence's meaning. And then it's the decoder's turn. It starts to generate the new text, the translation. And for every single new word it writes, it's doing two things at once. It's looking back at the words it just wrote to make sure its own sentence makes sense, and it's constantly looking back, or attending, to that rich understanding the encoder built. That's its roadmap. That's how it stays on track and generates something that's actually relevant and coherent.
So there you have it, from turning words into numbers, to giving those numbers meaning, and finally to solving the puzzle of context. It was that attention breakthrough that really unlocked the door to the incredible language AI we have today. And it really makes you think, right? If attention is the secret sauce for understanding our language, what's next? What will these AIs learn to pay attention to beyond just our words, out in the real world?